Hello calculus students, here we are with log functions in differentiation. This time we're going to split up into two parts because the log derivative is a little trickier. Alright? Now here's our log function, the natural log of x, with a vertical asymptote here. And so if we're going to sketch the derivative, I'm going to put on the same set of axes this time. Let's get some key points. Notice here at x equals 1 we have a slope of 1. Let's plot that. At 1 you get 1. At 2 looks like a slope of half, 1/5. And we're getting what we expected, that is, since this is concave down, we're going to get decreasing. Since it's increasing, they're all going to be positive slopes. And at 3, it looks like somewhere between 0.3 and 0.4. Let's say about 0.3. And at 4, let's just jump to 5. At 5 looks like 0.2. So that's essentially a fifth. So you see a pattern here? 5 went to a fifth, 3 went to a third, 2 went to a half, 1 went to 1. What do you suppose is going to happen at a half? At a half we get a slope of 2. So it's doing the reciprocal. And we get something that looks like, as we said, since it's concave down, it's decreasing. Since it's increasing the whole time, the derivative is positive. And that vertical asymptote is repeated. And it looks like 1 over x. Looks like the derivative is 1 over x. Okay, let's see why. We're going to use some implicit differentiation here. That is, we've got e to the y equals x, and let's take the derivative of both sides with respect to x. The derivative with respect to x of x. Let's see what happens. Well, we just saw from before the derivative e to the y is e to the y. But now we have to use the chain rule and multiply by the derivative of the inner function, which is y. So we get e to the y times dy dx equals, the derivative with respect to x is just 1. So dy over dx equals 1 over e to the y, but notice e to the y equals x. So there's your proof. That's why the derivative of the natural log is just 1 over x. Nice handy result there. So let's find these derivatives, the natural log of 2x. So if y equals the natural log of 2x, now there's a couple of approaches we can take here. We could use log rules first. Y equals the natural log of 2 plus the natural log of x. And now do the derivative. Now the natural log of 2, this is just a constant, so the derivative is 0. The natural log of x is just 1 over x. So we get 1 over x that way. But you can also go to the derivative right away and say, okay, I'm going to take 1 over everything inside the natural log times the derivative of the inner function, which is 2, and you get 1 over x. Now be careful on b, though. We can't use a rule of logs right away because you can't distribute logarithm over addition. But what we can do is go ahead and take the derivative. If this is y, the derivative is 1 over everything inside the logarithm times the derivative of what's inside the logarithm, which is 2x. So we get the derivative is 2x over x squared plus 1. Oh, here's a few more. X times the natural log of x. Well, that sounds like product rule to me. Product rule. So y equals x natural log of x. So y equals, let's leave the x alone, multiply by the derivative of the natural log of x, which is 1 over x. Now I'm going to take the derivative of x, which is 1, and leave the natural log of x alone. So we get y equals 1 plus the natural log of x. And then for part D, y equals the natural log of x quantity cubed. Now notice the cubing is not inside the log. If it were, then I might use the rule of logarithms right away. And I'll show you that with a part E. So the derivative is 3, leave the inner function alone, squared. So I took the derivative of the outer function. Now let's deal with the inner function, which is natural log of x, and I've got to multiply by the derivative of the inner function, which is 1 over x. So we get for the derivative 3 natural log of x squared over x. Now let's just make a part E here that's slightly different. Natural log of x cubed. Now when I write it like that, it just means I'm cubing the x inside. So again, you can take two approaches. Using log rules first to change it to 3 natural log of x, which is probably your best bet in this case, because then this is just a constant multiplier, 3, and the derivative of natural log of x is 1 over x. You get 3 over x. The other approach is to start doing the derivative right away. And so you got 1 over everything inside the natural log. So that's 1 over x cubed times the derivative of the thing inside the natural log, using the chain rule, 3x squared. So you get the derivative equals 3x squared over x cubed. And again, you get the derivative as 3 over x. Now, here's where log properties come to your aid here. This really gets to be a complicated inner function. So it really helps to start off with a log property. That is, think of this as x plus 1 to the half power. And then the bump the log rule says you can put the 1/2 down in front outside, making for a much easier derivative now. The 1/2 is a constant multiplier instead of a power. So it's 1/2. So the derivative of the natural log is 1 over whatever's inside. So we put that x plus 1 in the bottom, times the derivative of the inner function, which is just 1. So we get the derivative as 1 over twice x plus 1. Now it's really going to help here, because can you imagine you've got the product rule to do inside here, you've got an inner function, but if we use log rules right away, it's a natural log of x plus the natural log of the square root of 1 minus x squared. And just as we saw in this last problem, this square root is a 1/2 power, so it can come outside as a 1/2 multiplier. And then you got to know when to stop with your log rules. You can't take the log rules any further. There's no log of a difference. Still, this makes for the much easier derivative. So now y prime is 1 over x, plus the half is a constant multiplier, 1 over everything inside the natural log, times the derivative of the inside the natural log, which is negative 2x. So we get for the derivative 1 over x plus negative x over 1 minus x squared. And you can stop there. I mean, you can try and get it into one fraction and so forth, but that should be fine for now. Oh, here's more. This is where you really want to break it down and say y equals the natural log of x plus the natural log of x squared plus 1 squared minus the natural log of the square root of 2x cubed minus 1. So that's an example of the product and quotient rules of logarithms. The log of a product is the sum of logs. The log of a quotient is the difference of logs. Now, I'm going to use the power rule. Bring this 2 down in front. And as we said before, this is like a 1/2 power, so it's 1/2 natural log of 2x cubed minus 1. Now the derivative is much easier. 1 over x plus 2 times 1 over x squared plus 1. Let's not forget the derivative of the inner function, which is 2x, minus 1/2 times 1 over 2x cubed minus 1 times the derivative of the inner function, which is 6x squared. So we get 1 over x plus 4x over x squared plus 1 minus 3x squared over 2x cubed minus 1. Now, finding relative extrema. This could be tricky. There's our graph. We've already got our answer there. But let's just check it by hand here. Y equals the natural log of x squared plus 2x plus 1. So we can't use log rules to break this down because it's the log of sums. If it's a log of a product or 1 power inside the whole thing, but that's not the case here. So go to the derivative, which is 1 over whatever's inside x squared plus 2x plus 3 times the derivative of our function, which is 2x plus 2. 2x plus 2. So you've got the derivative is 2x plus 2 all over x squared plus 2x plus 3, a rational function for the derivative. And we want to know where it's 0 or undefined. Well, x squared plus 2x plus 3, looking at this quickly, can y prime equal undefined? You'd have to have x squared plus 2x plus 3 equal to 0. And a quick look at the discriminant, b squared minus 4ac, 2 squared minus 4 times 1 times 3, that's negative 8. That's less than 0, so you only get imaginary answers. So no. We don't have to pursue that. And that certainly seems to be the case here in our picture. So it's basically a happy parabola, this original thing. And you can always take the log of a positive number. So there are no restrictions on the domain in that case. But can we set the derivative equal to 0? So let's set the numerator 2x plus 2 equals 0. And sure enough, 2x equals negative 2, x equals negative 1. So at negative 1 we have either relative max or relative min. Now at this point you could try going in either direction. I think the first derivative test works a lot better because I don't want to have to do a second derivative of this huge rational function. And I've already got my first derivative. And we can try easy things like 0. Let's try x equals 0. The derivative is what? Just need the sign now. If I put 0 into this, I'm going to get 2/3. So therefore, since the derivative is greater than 0, f prime of f of x is increasing. And if we try x equals negative 2 in this function down here, now you got negative all over positive, so that equals a negative. F prime of negative 2 is less than 0. So therefore, f of negative 2 is increasing. I'm sorry, if it's negative, it's decreasing. F is decreasing at x equals negative 2. So there's our proof that it's a relative min, because you went from a negative derivative to a positive, which means you went from decreasing to increasing. The old first derivative test. Now, logarithmic differentiation is optional, and that's a trick where you can take the log of both sides first, and then you might get something you can do a derivative of. And here's an example where you have x minus 2 squared over square root of x squared plus 1. Now, you could do that by hand, right? But it's a huge mess. By taking a log of both sides, you break it down to easier parts, and then you do implicit differentiation, and it works out a lot nicer. One thing you have to watch out for at the end is that a lot of times, like in this case, you get y prime over y when you take the derivative of the natural log of y. So you'd have to multiply both sides by y and replace y with what it is, just to get everything in terms of x. It also is very handy for things like x to the x power. Same thing with derivatives involving absolute value. There's a special rule if you take the natural log of the absolute value, you still get the same answer, u prime over u, as long as u does not equal 0. Okay, and there's the example. Now if you have bases other than e, here's the derivatives of the exponential powers that we looked at. And basically, it's based on this chain rule here that you can write a to the x as e to the natural log of a raised to the x. Because that's what x is, log base. Or here, the a is written as e to the natural log of a to the x. And so the natural log of a becomes a coefficient on there. So as part of the chain rule, you're going to have to multiply by the natural log of a. And that's also how you deal with log base a of x. So feel free to write these rules down. It's how do you deal with this if you have bases other than e. So let's try this. On a here we have y equals 2 to the x. So the derivative, using this rule, is going to be the natural log of the base times just the exponential function, 2 to the x. That's all there is to it there. For b, y equals 2 to the 3x. The derivative will be the natural log of 2, because it's not base e, we have to multiply by that sort of correction factor, times the original function, 2 to the 3x, but now you got to multiply by the derivative of the inner function, which is 3. So 3 natural log of 2 times 2 to the 3x power. And for c, y equals log base 2 of x squared plus 1. The derivative is, well, we're going to still have that 1 over idea of x squared plus 1. But you also have to put in the denominator here the derivative, or the log of the new base here that's other than e. So you have the natural log of 2 down here. I'm pretty sure it's in the denominator. Yeah, it's in the denominator there. Now we still have to multiply by the derivative of the inner function, which is 2x. So we get for the derivative 2x over natural log of 2 times x squared plus 1. Okay? Now, here's just a little extra thing that we used to just say the power rule is true for integers. Now it's true for any, or irrational numbers. Now it's true for any real number. And I also bring this up because of this comparison here. Notice if you got e to the e, you don't use any power rules or anything like that. It's just a constant, so the derivative is 0. The derivative of e to the x is just e to the x. But if you have x to the e, now you go back to using our old power rule, because it depends on where is the unknown. If the unknown's in the power, it's an exponential rule. If it's in the base, you use the power rule. If the unknown's in both, then you can do this log differentiation trick. So you take the natural log of both sides. The x comes down in front. Now you can use implicit differentiation in the product rule here, and then multiply both sides by y, and you get this very bizarre answer here. X to the x times 1 plus the natural log of x. Okay? And again, I've limited the exercises to just what you might expect on the test. Flange, out.